We've been taking a look a lot about exponential growth and decay, and one specific sort of decay problem that comes up a lot in chemistry, biology, applied sciences is a half-life. The idea of a half-life means how long does it take for half of a population, half of a radioactive element, to be able to become deceased, okay, or to evaporate. So um, an example of this would be, and I'm going to show you two ways to do this. If it's an easier problem or a harder one. This one's a little easier. But the half-life of radioactive element um, unobtainium is 41 is 10 seconds. And if 256 grams of unobtainium are initially present, how many grams are present after 10, 20, 30, 40, 50 seconds? All right, so if the half-life is 10 seconds, essentially what that means is every 10 seconds, the initial amount gets cut in half, right? So for letter A, this is actually really easy. We would just take 256 and divide it by 2, and that would be 128. And I'll show you, if you have some not so nice numbers, how to take care of this in a few moments. For letter B, what we've done is we've actually gone through two half-lives. Okay, so what we would do is we would just take the 256 and we would divide that by 4, all right, because we've gone through two half-lives. So 2 times 2 or 2 squared. And that's going to be 64. And by the way, this is all in grams. Right? For letter C, since we have a third half-life, that would be 256 divided by 8, or that's going to be 32. And you can see how this works. The next one, D, is going to be 256 divided by 16, because it's another half-life. So we just keep multiplying the denominator by 2. That's going to leave us with 16. And then finally, after 50 seconds, we've gone through 5 half-lives. Okay. The way to think about that might be 256 divided by 2 to the 5th, or 256 divided by 32, which is going to end up being 8. All right. Now, if we want to write this as a function for half-life, okay, and this is probably more of the way you want to try to write these, is that we could say that the amount after time t is going to be equal to 1/2, or the initial amount, excuse me. So our initial amount was 286 or 256. And we're going to multiply that by 1/2 times t over 10. And what this is going to do is we have the half-life. We have that 10 seconds is going to be the half-life of that. So every 10 seconds, there's another half-life. So for instance, after 40 seconds, we could say A at 40 is going to be equal to 256 times 1/2 to the 40 over 10. Right? And if we shove that into our calculator, it should give us this 16. Okay, so I'm going to clear all this out. And we have 256 parenthesis 1/2. And we're going to raise that to the 40 over 10. All right. And notice it gives us 16 for that. All right. And every time I change it. So remember the first one we had 10, that was 128. All right. So that's going to be there. And I could just keep changing this numerator. All right. So that's like a general model. So we had, after 30 seconds, there were 32 grams left. All right. So this is like a general model that we can use for half-lives. All right. A general formula we can use is A of t equals the initial amount 1/2 times t over whatever the half-life is. I'm just going to call it HL, the half-life amount. All right. And that's usually a nice formula that'll work for us to be able to figure out what the half-life is. Or I'm sorry, the amount after time t given the half-life. This one we just want to complete the table. So we're given the decay rate is 7.6, but we're not given an initial amount, and we're really not given anything with respect to time of this. Right? But these are actually fairly easy problems. All right, so we know that K 7.6. Let's rewrite that, and we're going to make that into 0.076. All right, so we want to take and rewrite that as a percentage. All right. So that's going to be our K, and that's going to be the half-life of this. So what we're going to do is we're going to, or not even the half-life. So for us to figure out what the half-life is, we're going to make an exponential model, and we're going to use our old A sub 0, or I'm sorry, A equals A sub naught e to the kt. All right, but in this case, the half-life means that A is going to be half of the initial amount. So that actually makes it pretty easy because we could set this up as 1/2 A sub 0 equals A sub 0 E. The decay constant is 0.076, and then that's going to be T. And what this should do is help us solve for T pretty easily. All right, so the A sub zeros, we can divide both sides by A naught. That's going to go away. We can take the natural log. So we have ln of 1/2 equals 0.076, or e to the ln of e to the 0.076. Ln of e to the 0.076t. Ln's and e's cancel each other out. And then we can divide both sides by 0.076. Right? So ln over 1/2 divided by 0.076 is going to be equal to t. And we should probably approximate it to figure out what the half-life is. And it's going to be in years, all right, because we're given it to us in that unit. So if we go to our calculator, we have the natural log of 1/2, and we're going to divide that by 0.076. All right. And that gives us a negative 0.9.12. All right. Um, that's just because that's the decay rate. This is should be a negative. It's the decay rate, so that would be a negative. So the half-life for this would be our 9.12. All right, years. Okay, so 9.12 years. Now, of course, if you don't believe your answer, what you can always do is pick an initial amount and just throw it into the formula and then throw 9.12 back in. Okay, so let's just check this before we go on to the next problem. And let's just say we have an initial amount is 100. All right, so what we can do is we would just throw that into our model and then also throw 9.12 in there, and we would say, and we would check to see if 100 is the initial amount. We should have 50. All right, so this would be 1/2 e to the negative 0.076 because it's decaying times 9.12. And that should give us about 1/2 of 100, which is going to be 50. All right, so this is just a way to check. So let's go into our calculator, and we're going to have 100, and then we have our e to the negative, and I'm going to put this in parentheses, negative 0.076 times 9.12. And look at that, it gives us just about 50, okay? And the reason we don't get exactly 50 is because, well, we rounded off the answer. All right, so that's just a way you can check just to make sure that your answer makes sense. Just make up an initial amount, plug it back in, and you get half of that amount. If we want to go the other way and we want to try to find the decay rate, well, this time we're given that the half-life is going to be 20.3 weeks. So that's going to be our T. So in this case, T is going to be 20.3. And let's just say that our amount A is 1/2 of the initial amount. And so that means that we're going to have 1/2 A sub naught is going to be equal to A sub naught E to the K times 20.3. We can divide both sides by a0. We can take the natural log of both sides. So ln of 1/2 is ln of e to the 20.3k. We can divide both sides by 20.3 to solve for k. So ln of 1/2 over 20.3 is equal to k. And then let's just throw that into our calculators. All right, so that's going to be, clear this out. We have ln of 1/2. And we are going to divide that by, we said 20.3, I believe. Yep. So divide 20.3. And our decay constant is 0.0341. All right, negative. All right, so that's going to be negative 0.0341. That would go right in here. Okay. All right, so hopefully that's not too difficult. Okay, just our applications of some decay. We have one more problem before we can move on to our logistic model, but we're almost done with this growth and decay stuff, which is probably the most important stuff within this section.